Hello, in this video we'll explain additional statements in VHDL. To be specific, we will introduce the for generate loop as well as implementing sequential design using VHDL. First, we will provide an example on the for generate loop to illustrate its idea. Then we will revisit the process block as it's useful or important when it comes to implementing sequential design in VHDL. Next, we'll implement some additional or introduce some additional syntax tips in the language VHDL. We'll next move to implementing a finite state machine diagram using VHDL code and briefly touch on how to test FSM code in ModelSim. We'll introduce new additional analyses in VHDL related to sequential design. Namely, we will explain the steps needed to obtain a maximum frequency and the steps needed to obtain the state machine viewer. To illustrate the idea of the for generate loop, we will use the example of a 4-bit adder generated using this structure. First, we have a diagram of a 4-bit adder, and within the architecture part of the code, we're declaring the full adder to be used as a component, and then we're declaring C as the vector to hold the carry-in signals such that it passes the first carry-out, which is C0, to the next carry-in, which is CN1, and so on. So the signal C here is actually used for the connection between the different instances of the full adder, as well as to take on the value of the port Cn and feeds it into the first full adder FA0, which is the first full adder on the right. C4, which is the last bit of signal C, is passed directly to Cout, which is the port Cout from our 4-bit adder. Within the for generate loop, we have the iterator variable I, which starts from 0 and stops at 3. Notice here, within the for generate loop, we only call this line once or type it once, but it's actually being generated 4 different times for I starting from 0 to I equals 3. Without the for generate loop, this full line will have to be repeated, of course, 4 times, such that here we're going to write FA0, full adder, port map, A0, B0, C0, and so on. Notice how the last signal in the port mapping is CI plus 1, such that when it comes to the next iteration, this CI plus 1 will be used as the carry-in. This will account for the fact that every Cout of a full adder is used as Cin of the next full adder, while the last Cout, which in this case is going to be C4, is connected as Cout, which is the port in the main 4-bit adder entity. The for generate loop is different from the for loop in the sense that it is being used to replicate different or multiple hardware blocks. In this case, we're replicating the full adder 4 times, and the number of replication can be changed by changing the range we used for the for generate loop, which is in this case from 0 to 3. Now this is just a revisit on the process block, since it's going to be used later with the FSM implementation. It is important to remember to include control structures such as if statement and case statement within a process block. The process block typically has a list of variables These variables are usually input ports to the design or signals within your design, such that the process is only sensitive to these variables, meaning the process will not be evaluated or updated unless one of the items or one of the inputs or signals mentioned within the process block sensitivity list change. So in this particular example, the process will only be evaluated when A or B, or both, of course, change. Before we jump into explaining finite state machine implementation in VHDL, it's important to go over some additional syntax tips in VHDL. First, just like arrays, we have to declare states as a new data type within the language. Remember, the only built-in main data types in VHDL that we will use are integers, which are the 32-bit variable, and standard logic, which allows you to choose between 0 and 1 for 1 bit, and standard logic vector, which allows you to use multiple bits within a vector. You have to state the vector size and so on. When it comes to states, just like arrays, we have to declare the state as a new data type, and the structure goes as follows. So first you have to write type followed by state, and then you say is. After is, you need to list all the state names that you want in your design. Okay. So in this case, or in this particular example, the assumption is that we're implementing an FSM that contains two states. The state names are S0 and S1. The second line in this state type declaration is creating a signal named current state and another signal named next state, which are of type state. So they are of type state. And then remember, this is the initialization operator. We're basically initializing the current state and the next state to have the value of S0 at the startup of the system. So the initialization operator is used to assign values once the device is powered on. In this case, before any input is received, the current state and the next state variable will hold the state S0 in them. Next, we're going to have two processes within the FSM design. The first process is called the sequential process. Typically, it has to be synchronized with the clock. That means updates only occur on the rising edge of the clock, or let's say the falling edge of the clock. That's why the process list only contains the clock signal. So changes will only happen, or updates will only happen with the change of the clock, with changes to the clock. Within the process, we're going to check if this change occurred or happened due to a rising edge of the clock or a falling edge of the clock, and so on. So we're going to have to use an if statement within this synchronous sequential block. In case of an asynchronous reset, meaning if you want your design to reset at any moment in time, regardless of the clock, without having to wait on the clock, then you need to mention the reset input, or RST in this example, as part of the process sensitivity list. The second example here simply says you want to update your signals or the state of the system or the output, whether the clock rises or a reset occurs at any moment in time. Of course, if reset occurs, we have to reset the system accordingly. If it's let's say a rising edge triggered system, you're going to update the next state based on the different inputs and so on. Here we see an example of the implementation of an FSM diagram containing two states. The diagram we're trying to implement, or this code implements, is shown on the left side. Before implementing the design or even testing it, it is important to know how to read the design and interpret it. First of all, we have multiple states in an FSM diagram. This particular diagram contains two states named S0 and S1. Typically, every state is represented using a circle. At the top of the state, you see the state name. Here we have a state named S0 and another state named S1. At the bottom half of every state, you see the value of the output. Sometimes you see the value with its variable name, meaning y equals 10, for example. Or in this particular case, the assumption is that the output is called output. Okay, so we have a circle to represent each state. The top half of the circle puts the state name. The second or the bottom half of the circle shows the output of this particular state. So every state will have a specific output to be updated. And you have also arrows on the diagram or in the diagram to indicate where to go after each state. So for example, with the help of the arrow, we can understand that at startup, the initial state is S0. So once we reset or restart the system or power it on, we're going to go to S0. And then when we are in state 0, the next state following the arrow here is going to be S1. Sometimes, depending on the diagram you're provided, you will have arrows with labels on top of them to indicate the condition that allows you to move between states. For example, in this diagram, there's no condition for moving to the next state besides, of course, the clock, the rising edge of the clock, for example. So we know on the rising edge we're going to go to S1, and then after S1 on the rising edge we will go to S0. But sometimes you will see on the arrow a value of an input. For example, 5. Let's say here it could be A, as in your input is equal to 5. This means we can only go from S0 to S1 if our input A is equal to 5. So you're going to need to check for A, the input. If it's 5, you go to S1, otherwise you do something else. So there's going to be an if statement within the code to check the input. To keep it simple for this example, we are limited to just the clock as the only input port. The assumption is that the system has no reset, as written within the description. So we do not have a reset and we do not have an additional input besides the clock. However, we do have an output, and we can see that the output contains 2 bits. So in VHDL we're going to mention this, or we're going to declare this output using standard logic vector. For 2 bits it has to be 1 down to 0. Now, while explaining the code, I'm going to try to highlight any part that is necessary to modify or update as you are implementing a different FSM design. First, this is just the architecture part. Of course, for the entity, you'll have to declare the entity name, the different inputs and output ports. Of course, the clock has to be an input for this design. We have an output which we named output, and it's a vector 2 bits. If we do have a reset, we're going to need to add a reset as an input. If we have an additional input, depending on its type, we're going to need to declare it with its data type. Okay. Now, we're going to start by mentioning the entity name within the architecture. In this particular example, it's called FSM. You could be implementing a counter, so you need to change the name to counter, for example. Or if you're doing FSM2, an entity name FSM2, this part of the code needs to be changed to FSM2. Next, here we're declaring state type. Within it, we have to list all the states within our state diagram. For this particular design, we have state 0 and state 1, S0, S1. If your design does not have S0, S1, then you have to remove S0, S1, replace them with the correct state names. It could be a state named start or a state named idle state or waiting state, for example, all with one word without any space. So all the states need to be listed within this line of code. The next line, which creates variables to hold the current state and the next state, this is going to be a signal of type state. The next line here creates these signals and initialize them to be having a value S0, because from the diagram you can see there's an arrow pointing at S0. So this indicates that the initial state at startup is going to be S0. So this part of the code can be modified to the correct state that you want to be the initial state, or you can remove it in case you do not need to initialize the first state. Next, we have the clock process, or the sequential process part of the code. If your design has a reset input, this is where the reset input needs to be added first, and then the reset input needs to be checked within this process. If you're resetting, of course, you need to make sure that the current state goes to S0 for this particular example. In this case, we do not have a reset, so I'll explain the code as it is. We're checking if rising edge of the clock. So process clock simply means monitor any change that happens to the clock. If the clock changes, then update or evaluate the process. Since the clock could be rising or falling, or it could, for a clock, it could either be rising or falling, then you need to check within the process if it's a rising edge or if it's a falling edge, depending on the application. So imagine this is the clock signal. I'll use a different color. So the clock changes continuously between 0 and 1, from 0 for this sketch, and then 1, back to 0, back to 1, and so on. For the code that we have here, we're simply saying only update the current state at this particular moment in time, when the clock goes from low to high. So we're saying if rising edge clock. You could change rising to falling accordingly. I'm going to keep it rising for this example. And you will always say current state equals next state. So this part of the code is going to remain unchanged for any FSM that has no reset. If you do have a reset, you're going to modify the if statement slightly such that you force the current state to go to the reset state before you check the rising edge. We're going to see a different example through the lab sheet. Now when it comes to the second process, which is called the combinational process because it has no sequence, it has no history or memory. So based on the current state or the input if available, you're going to update the next state. And so I give you the current state, you can immediately tell me what the next state is going to be and what the output is going to be. This part of the code, this line of the code, if you have an input other than reset, of course, this input should be added to the sensitivity list of the combinational process. You're going to say process current state, comma, whatever name of the input is. So this is the second modification that we'll make. Then you will always use case statement to monitor the current state. And then based on the current state, whether it's S0 or S1, you will decide on what the next state is going to be. So for this particular diagram, when the current state is S0, the next state is S1. You just follow the arrows in the diagram. For this particular diagram again, S0 output is 1, 0. So here we're saying output equals 1, 0. You could have an output named something else. It could be called y equals 1, 0. Or it could be an integer. In this case, you will say output equals 2. You can write 2 right away without the double quotes for integers. Note that this part of the code, the when S0 until output here, will be repeated for every state in the diagram. So right after it, we're saying when S1, when the current state is S1, what we will do is we're going to make sure that the next state variable contains or stores in it S0. This is the next state after S1. And we're going to make sure to output 1, 0 because we will output 0, 1 because 0, 1 is the output of state 1. So when the current state is S1, make sure you output 0, 1 and update the next state variable for the next cycle to be S0. Now, besides the highlighted part of the code, depending on if you have an input, you will also need to add a conditional statement to surround, I will highlight it in blue, to surround the next state, such that you update the next state based on the condition. So you will see here, let's say an example, you will see, let's say 1. Okay, you're going to write when the input is equal to 1, or if input equals 1, then next state is S1, else something else. So sometimes the next state updates conditionally based on a specific value of the input. If that's the case, you will see a value on top of the arrow. Here, these arrows. And that means you will have to modify the code to include an if statement right here. Based on the if statement, based on the inputs and the current state from here, you're going to update the next state. When it comes to testing FSM code in ModelSim, it is important to note that the clock port has to always be clocked, and this is actually the only time we use the clock for its proper purpose in ModelSim. And remember to always use force for reset. The goal of testing the reset in ModelSim is to make sure that while reset is triggered, for example, while reset is 1, the system goes to the reset state. And then whenever reset is disabled, whenever reset is 0, for example, we're going to update the system normally without getting stuck within the reset state, for example, state 0. So that's why we will always try to reset the system once at the beginning by making reset 1 and then changing it back to 0. If your goal is to test reset, making sure it works at any moment in time, then keep reset 0 for a while. Make sure you go to multiple states and then make reset 1 to check that it actually, the system actually goes to the reset state successfully. To test correct transitions among or between states, we're going to have to test different input combinations or different input sequences while observing the state diagram to see if for different inputs the next state updates correctly based on the diagram provided. This is better illustrated through an example, or while implementing it you will have a better idea of it. You can view the state machine you implemented in Quartus by going to the Tools menu, choosing Netlist Viewer and then State Machine Viewer. You will obtain a diagram very similar to what you see on the screen. But again, it's important to make sure that the FSM code that you're working on is the top level file, and then you compile and then you run the Netlist or the State Machine Viewer. Next, for the maximum frequency analysis, you can check the maximum possible clock frequency your system can handle by going to the table of contents panel. So after compiling your project, you can go to table of contents and select time quest timing analyzer. You need to expand this first, and then you will find multiple red text or red options they will say slow and then some voltage and then some temperature model. You will choose the model with the highest temperature. In this particular example, it's the first option. Then you expand this option and then you click F Max Summary. The part of the screen we're interested in for the screenshot will be just this part of the screen. That's it. Thank you for watching.